Welcome to Mr. Tompkins Ed Tech and my series of exam question compilation videos on key topics you might still be struggling with. This particular video covers distance time graphs and speed time graphs. I've taken related questions from my past paper walkthroughs and given them to you here back to back. This series is intended for the last few weeks of your revision, and my advice is to go through all the practice papers and past papers before you look at these, or the compilation videos will be the mathematical equivalent of endgame spoilers for you. Having already worked through all the practice papers, these compilation videos will give you a deep dive on topics you are still finding challenging, give you more of an overview, helping you recognise command words, identify key features and strategies, building your confidence and helping you apply these techniques for future papers. If you find it helpful, please give the video a thumbs up, it will really help me out. Also, if you haven't already subscribed to my channel, why not do that now? I'll be making lots of these compilations over the next couple of weeks and you'll get notified of these as soon as I upload them. Right, let's get into it. Question 9 concerns itself with this distance time graph. Now this is showing a race between three boys, Alan, Ben and Carl, over 1,000 meters. So we've got the time along the bottom and we've got the distance along the side. Okay, so normally who wins the race is the person who gets to the finish line first. So we should be looking at which of these three boys gets to the 1,000 meter mark before the others. So the 1,000 meter mark is here, this line. So I'll quickly draw that on. This is the finish line here. So you can see that Ben reaches it here and then Alan and Carl reach it at the same time here. So the person who gets there first is Ben. He gets there at this point here at 4.5 minutes. So who won the race? Ben. So Ben won the race. Why? Because Ben finished after 4.5 minutes and Alan and Carl finished after 5 minutes. Okay, now the next part of the question asks us to describe the race, and it's worth 4 marks, so we need to come up with at least 4 statements about the graph. So we can read this graph from left to right, so you can see that as we start off that Alan starts off the fastest, so Alan is in the lead, then Ben is second and Carl is third for the first part of the race. At this point, at 2.5 minutes, Ben slows down. At 3 minutes, Alan stops for a while and then starts again soon after at a slower pace. At 3.5 minutes, Ben speeds up and then overtakes Alan. Carl speeds up at 4 minutes, but it's not enough to overtake anybody, but he does finish the race at the same time as Alan. So writing all that down in the question paper, at the start of the race Alan is fastest. After 2.5 minutes Ben slows down. After 3 minutes Alan stops. After 3.25 minutes, Alan starts again but slower than before. After 3.5 minutes, Ben speeds up. After 4 minutes, Carl speeds up. After 4.25 minutes, Ben overtakes Alan. After 4.5 minutes, Ben finishes. And after 5 minutes, Alan and Carl finish. So you can see I've written all those down just in chronological order, making a note of any changes along the way. Question 8 gives us a distance time graph showing the journey of a toy train, and underneath we have 4 possible descriptions of the first 2 parts of the journey. Now let's have a look at the first two parts of the journey. This first part here is a straight line, and it is increasing as time increases, so it's sloping upwards. So that indicates that the toy is moving at a constant speed. And then the next part, the distance isn't changing for a period of time, so that would indicate that the toy train is at rest. So which one of the descriptions most accurately displays that? It must be B, moves at a constant speed and then is stationary. Okay, for part B, it says work out the average speed for the last 4 seconds of the journey. So average speed, if you remember your DST triangle, average speed is equal to distance traveled divided by time taken. And from our diagram, the last 4 seconds is this part of the graph. Well, we know the time. The time is the 4 seconds. So this is how much time it takes, 4 seconds. And the distance traveled then is going to be the distance from 4 to 10, which is a distance of 6 meters. So it's gone 6 meters in 4 seconds. So then average speed then is going to be our 6 divided by 4, which is 3/2 meters per second. Question 24. A ball is thrown from a point 6 meters above the ground. The graph shows the height of a ball above the ground in meters. Now 6 meters is probably about roof height of a house. So imagine you're standing on the roof and you throw a ball off the roof. The first part of the journey, the ball is going to go upwards, but then due to gravity it starts then fall into the ground and it hits the house, hits the floor a fair distance from the house, something like that. Okay, what we need to do though is to estimate the speed of the ball in meters per second after 1 second. Okay, now after 1 second the ball is at this point on the curve, isn't it? Okay, now we've got a distance and time graph here essentially. It says height, but it's actually distance from the ground, isn't it? So our speed is going to be equivalent to the gradient of the distance time graph at that point. So what we want to do, because this is a curve and not a straight line, is to draw a tangent on it with our ruler. So you just kind of put your ruler on the curve, so it's so it's just touching the curve, and you've kind of got equal space either side of it, kind of here and here between the line and your curve. So once you're happy with where your tangent lies, you can draw it on. Okay, it's going to look something a bit like that. And we're going to need to take 2 points on it and evaluate the change in y and the change in x. Now I would suggest you take a point which lies on one of your known grid references. So I'm going to take this point here that is exactly at 2, and this point here which is exactly at 0. So I'm taking a good length of the line, and so I can be quite accurate. Don't want to put your points too close together. So that's going to be my change in y, and then my change in x. Is here. So how far is, well, my change in x is easy to do. It's just 2 subtract 0, isn't it? I'm going to quickly do that first. That's 2. What's my change in y? That's a little bit more tricky to read. So that point there, I think, is 2 little squares above 9. Now there are 5 divisions between each unit, so each one must be worth 0.2. So I reckon that point up there must be 9.4. The base of the bottom point of my y line is halfway between 6 and 7. I'm saying that's going to be 6.5. So then the change in y is going to be 9.4 subtract 6.5, which is 2.9. Okay, so then the gradient. So the speed of my ball is going to be equal to the gradient, which is change in y divided by change in x, which was 2 subtract 0 on the bottom and 9.4 minus 6.5 on the top, which was 2.9 over 2, which gives me 1.45. Now, the height was in meters and the time was in seconds, so this must be meters per second. 1.45. Question 6. A ship is sailing in a straight line from its home port. The distance time graph shows 4 hours of the journey. And we've got the distance from the port up the side here, and that's in miles. And we've got the time along the bottom, and that apparently is in hours. Okay, and now we're asked to work out the speed of the ship during these 4 hours. Now, you hopefully remember the relationship between distance, speed, and time. If you don't, this handy triangle is quite useful. DST triangle. You notice they're in alphabetical order. DS and then T. And then you can cover up the thing that you want to find and work out the formula used in the other two parts. So work out the speed of the ship during these 4 hours. So we want the speed, which is this one here. So we cover up the S, and that tells me what to do with the others. So average speed is distance traveled divided by time taken. Okay, so how much distance is traveled? Well, the distance traveled is, let's just triangulate a little bit so we can see what's going on a bit more clearly. So I'm just going to draw a triangle along here, up here. So then the distance travelled is this distance between here and here then, isn't it? So how far is it from there to there? Well, the top value is here. I've got 5 little squares between 100 and 120. So 20 divided by 5 is 4. So each one of those little squares is going to be 4 then, isn't it? So that top mark there is at 116. And the bottom one down here is 2 little squares up from 40. So if each one of those is 4, that's going to be 48. So then the distance travelled is going to be 116 subtract 48. What's that then? 52, 62, 68, isn't it? That's 68. And the time travelled then is this distance along here. That's a lot easier to work out. That's 4. Okay, so we travelled 68 miles in 4 hours. So if we divide one by the other, we should get the answer in miles per hour then, shouldn't we? So 68 divided by 4. 4's into 40 go 10 times. So 4's into 60 go 15 times plus another 2. That's 17, isn't it? So 68 divided by 4 is 17. Okay, so then that is 17 miles per hour. That's my final answer. Okay, question 23 has a speed time graph for a car journey. So we've got time along the bottom and speed up the side. And we need to estimate the acceleration at 6 seconds. Now, acceleration is the gradient of a speed time graph. So if we have a look at the graph at the point where t is equal to 6, so reading up from 6, we're talking about this point here on the graph. What is the gradient of the graph at that point? Now you notice it's a curved section of the graph, so it's not about taking 2 points on the line and working out the gradient. What we need to do is we need to take our ruler and draw on a tangent at that point. So we try and get the ruler to just touch the point so that the gaps between the ruler and the line either side are about the same, and then we can draw on our tangent at that point. Okay, and then we need to find the gradient of that line. Okay, so taking 2 points on this line, let's take this point here, that's the point 0, what's the scale here? Each one of those little squares is 1/5 of 2 units, isn't it? That's not very helpful. So 5 divisions between 2 units means that each division is 0.4, so I would read that one as 3.2. So this point, coordinate down here is 0, 3.2. Let's pick another one further up. Let's pick this point up here at 10. So when x is 10, or t is 10, what's that then again? It's about 3 squares up, so 10, 11.2. Okay, so then we need to work out what the change in y and the change in x are between these 2 points. So let's draw on a triangle. So how far is it in the direction of y? Well, 11.2 subtract 3.2 is 8, and in the direction of x, 10 take away 0, easy peasy, it's 10. That's a bit why I picked those points. So now I know that, I can work out the gradient of the tangent. So gradient of tangent at x equals 6. Gradient of tangent is equal to change in y, 11.2 minus 3.2 over 10 minus 0, which is 8 over 10, which is 0.8. So the acceleration then is 0.8 meters per second. So meters per second squared. Being very naughty here and writing over the lines. Don't do that in the exam. Part B wants us to estimate the average speed of the car for the journey. So we all know that average speed equals total distance travelled divided by time taken. Okay, so basically we need to know, we know the time taken, but the distance is what we're going to need to work out. Now you'll remember that the distance on a speed time graph is given as the area under the curve or under the graph. Okay, now this graph is made up of 3 distinct parts. I can divide it up into a triangle, a rectangle, and this rather more difficult shape here with a curved edge. This is the bit I'm going to have to estimate. I'm going to have to estimate the area of that section. Okay. Now, probably the easiest way, but most rough and ready way of estimating is saying, well, let's just assume, rather than having a curved thing like that, let's make it into a triangle and then work out those 3 areas. So working out this area, and the area of that triangle underneath there. Now obviously it's going to be a underestimation of the area because I've got that shape in the middle that I won't have calculated, but it's an estimate and I think it's going to be good enough for our purposes. So this area here is a triangle, so it's a half base height, isn't it? So that's going to be a half times 18 to 24 is 6 times a height of 12. So half 6 is 3, 3 6s are 36. This bit here is a rectangle, so just length times width. It's going to have an area of 14 to 18 is 4 times a height of 12. 4 12s are 48. And then this bit here is a triangle, so again half base times height, which is a half of 12 times 14. Half of 12 is 6. 6 14s, was that 84? Okay, so let's write that in our answer sheet. Is 84, 46, and what was it? 36, 48, and 84. 48, 84, and 36 over total time taken. Well, the time of the journey was 0 to 24, so it took 24 seconds over 24. So let's add that up. 84 plus 48 plus 36 is 168 divided by 24, and 168 divided by 24 is 7. So average speed is 7 meters per second. So 7. Okay, now the last part of the question says evaluate your answer to part B. Is it an underestimate, an exact value, or an overestimate? Well, as I said earlier, we have estimated this area under the curve section to be a triangle, so we've missed off this bit in here. Okay, so we have underestimated the distance that was traveled in the time taken. So if in our calculation the distance was low, then we've got a low number divided by a number, so this speed then is going to be a low. It's going to be an underestimate. So oops, it's going to be an underestimate. We need to write a comment with that, so so what did we do? We estimated area under curved section to a triangle which was less than the area under the curve. Okay. Question 27. Here is a sketch of a speed time graph for part of a journey. So we can see it's made up of 3 distinct areas. So the vehicle, or whatever it is starting from rest, is speeding up between 0 and the point A. Then it's traveling at a constant speed, and then it starts to slow slightly until it gets to the point C. Now, we are told in the question that the average speed from 0 to t seconds was 7.2 meters per second, and we want to work out the value of t. Okay, so from the average speed, we should be able to work out the total distance traveled in that amount of time. And we also know that the area under a speed time graph is equal to the distance traveled. And this distance is made up of 3 very easily calculable shapes. We've got a triangle, we've got a rectangle, we've got a trapezium. So what we're going to do is we're going to work out what the areas of these 3 shapes are, and we're going to compare them to the average speed, or the distance given by the average speed over that amount of time. Okay, So easy peasy. Let's give it a go. So using our DST triangle, so we know that average speed equals distance divided by time, so distance is speed times time. So the total distance travelled is going to be speed times time, which is 7.2 times the time taken, which is t. So it's equal to 7.2 t. So it's going to be an equation we're going to have to solve then, isn't it? Okay, and then coming back to the area then, but distance travelled is also area under graph, which in this case is going to be my area of my triangle plus my area of my rectangle plus my area of my trapezium. Okay, so area of my triangle is going to be half base times height, isn't it? So it's going to be half 8 times 9. My area of my rectangle is my, so that was 8, that was 9, wasn't it? Now the base of this, or the length of my rectangle, is going to be the difference between 8 and 14, which is 6. It's also got a height of 9, so that's going to be 6 times 9. And then my trapezium, to find the trapezium, you average out your two parallel sides, so it would be 9 plus 7 over 2 times the distance between them. Now that distance is going to be t subtract 14. Does that make sense? So it's going to be half of, I hate when I squish things up at one end, 9 plus 7 times t subtract 14. Okay, so half 8 times 9 is, half of 8 is 4, 4 times 9 is 36, 6 9s are 54, that was rather messy that I wrote down, but 9 plus 7 is 16, divided by 2 is 8, so that's 8 lots of t minus 14. And we know that that is the same thing as 7.2 t. So you'll see we've got an equation in t, which we can now solve. So let's do that. So 7.2 t is equal to, well, 36 and 54 adds up to 90. Then removing the brackets over here, I'm going to get 8t minus 8 lots of 14. What's that? 80 and 32, so 112. Now rearranging, so I've got all the t's on one side and all the numbers on the other. I think it would be easier to collect t's on the right, keep it positive, and then numbers go to the left then. So I'm going to get 112 minus 90 equals 8t minus 7.2t. So that's going to give me 0.8t on the right, and 112 take away 90 is 22. So 0.8t is 22. So then dividing by 0.8 should give me the value of t. So I make that t equals 27.5. Question 21. We've got a speed time graph which we're told represents the speed of a skier, and we're told that Nick wants to estimate the distance travelled by the skier in 140 seconds. Now distance travelled is the area under the graph, so we're going to have to work out what this area is. So he works out the area of the triangle with vertices 0, 0 and 140, 0. So 0, 0 is here, and 140, 0 is here, and the other vertex is at 99.8, 99.8, so the tallest point on there. So he's going to estimate this as a triangle like this. Triangles are easy to work out the areas for, whereas wibbly wobbly lines, not so much. Rulers give me jip. Okay. So, going to work out the area of that triangle rather than the wibbly wobbly area. Does Nick's method give a good estimate? Tick the box. I would say it does on the whole. You've got this bit here which is an overestimate, but it kind of matches up with this bit up here which is an underestimate. Those two areas are fairly similar. You've also got this little bit up here which is an overestimate, and quite a large area down here which is an underestimate. So if you do use this approximation, then I would say that the answer you're going to get is a slight overstatement of the distance travelled, because, as I say, this bit down here is bigger than this bit, so your area is going to be bigger than the area under the graph. However, so I'm going to say that overall that yes, I think it is a good estimate, and the reason for that is the areas above and below the lines of the triangle are roughly the same size. And I think that, along with the work I've done on the diagram, is going to be sufficient evidence for the 2 marks. Okay, so part B, use Nick's method to work out an estimate of the distance. Okay, so basically we just need to work out the area of that triangle then. So area of a triangle is half base times height. So the baseline is of length 140, which is from 0 to 140, and the height is 9.8. That's the height there, 9.8. So it's going to be half times 140 times 9.8. Which I get as 686 meters. Okay, Helen uses a different method. She starts by estimating how many of the smallest squares are in the region between the graph and the horizontal axis. Her estimate is 1,550 squares. Complete Helen's method to estimate the distance. So it looks like Helen had a lot of time on her hands then, and she's counted all these little squares that lie underneath the graph and added them all up, and she's found there's 1,550 of those. So in order to then take that and turn it into a distance, we need to know how much one of those squares is worth. So one of these squares has it's a square, but this direction on the scale is going to be 2 units, representing 2 seconds, and this unit on the scale is 0.2 of a meter per second. So in order to turn her 1,550 squares into an area, we need to work out the area of this, well, it's a rectangle actually, work out this rectangle and times it by 1,550. So area is going to be a 1,550 teeny tiny squares times 2 times 0.2. $620. Bit of a bonkers method, but there you go. Question 18. Here is a velocity time graph of a car, and we're asked to estimate the distance travelled in the first 10 seconds. Okay, so distance travelled is the area under a velocity time graph, so we need to estimate the area under the graph between 0 and 10. So we want the area under the graph to the left of this line. So we want this area in here. Now you can see that it's got a curved edge, which is not very helpful, but we can estimate the area by creating an approximate area that is similar to our original area. So if we put a straight line between there and there, we can estimate the area to be the area of that triangle. And obviously it's going to be slightly less than our true area, but it should be reasonably accurate. So area is approximately equal to that triangle, half base height, which is going to be half the baseline, which is 10, times the height of the graph at that point there. Was that 45? So 45 times 10 is 450, divided by 2 is 225. So I'm going to estimate it to be 225 meters. Question 23. Here is a velocity time graph of a motorbike for 25 seconds. After how many seconds was the acceleration 0? Okay, well the acceleration is going to be the gradient of the velocity time graph, and the acceleration is 0 when the graph is flat. So you can see, where is it flat? It's going to be flat here at this point here, or more in particular right in the middle of there. So at that point there, look, it's flat. So reading down to the graph, reading down to the axes below, it's there, isn't it? Now that is, well, you can see I've got 10 divisions between 0 and 5, so each division must be a half, or 2 divisions, or 2 little squares is 1. So I make that 6 then. So after how many seconds was the acceleration 0? It's going to be after 6 seconds. And then it says work out the distance travelled in the last 15 seconds. Now distance travelled is the area under a velocity time graph, and the last 15 seconds is, so 25 seconds less 15 is 10. So it's this section here. Right. Sort my pen out. So from here down to here. Now you'll see that this section of the graph is a straight line. Can't seem to draw on there. Okay, that's it. So this section here we're looking for. Okay, so that's the section of the graph is a straight line. So the shape we've got is a trapezium. So the area of a trapezium is going to be the 2 parallel sides added together divided by 2 times the distance between them. So this is my A value here, isn't it? Which is of a height 22. So A is 22. This is my B line on the other side. That is at a height of I make that 18. The distance between them is this distance. We said for the last 15 seconds. So it's that 15 there. So distance travelled is going to be a half a plus b times h, the formula for a trapezium, which was a half of 22 plus 18 times 15. Got those right? 22, 18, 15, yeah. So half of 22 plus 18. 22 plus 18 is 40 divided by 2. So half times 40 times 15. Half of 40 is 20. 20 15s are 300. So it's 300 meters. Question 24. Beth ran a 200-meter race. Here is a graph of the first 8 seconds of her race. She completed the race at a constant speed of 9 meters per second. Okay, so we've got a speed time graph here. And we're told underneath that Amy completed the race in 27 seconds. Did Beth finish before Amy? You must show your working. Okay, so we were told that Beth continues the race at 9 meters per second. So I can get a ruler out and draw the rest of her speed time graph. So it's just going to flatline after there. So the rest of the graph is going to be a flat line until she finishes. I'm not quite sure when she finishes. Maybe we should work that out. So she's got to cover 200 meters. Now we know that the area is the distance under the graph. So if I just draw a line there and work out the area that she covered in the first part of the course where she was accelerating. So that is a triangle. So the area under the graph is going to be a triangle of base 8 and height 9. So half base times height is going to be a half of 8 times 9. So 4 9s are 36. So she covered 36 meters in that first part of the graph where she was accelerating, which means that the other part of the graph, which is going to be a rectangle, has an area of 200 minus that 36 meters, which is 164. So it's going to have an area of 164. Now we already know that the height of the rectangle is going to have to be 9. So if I divide 164 by 9, I'll know the length of that rectangle. 164 divided by 9 is 18.2. So it's going to take her another 18.2 seconds to finish. So if she's at 8 seconds, then she's going to finish 18.2 seconds beyond that, which is at 26.2. So completing the graph unnecessarily because I've already got the answer, haven't I? But let's just finish it off for completion's sake. So 164 divided by 9 tells me that was 16.2. So she must have finished the race. So it was 18.2, wasn't it? So she must have finished the race at 26.2 seconds. So Beth finishes at 26.2 seconds. So did she beat Amy? Of course she did. She was 0.8 seconds quicker. So she does finish before Amy. Go Beth. Question 24. The speed time graph shows 20 seconds of a car journey. Harry wants to estimate the distance the car travels in this time. He uses a triangle and a trapezium as shown to estimate the area under the graph. Okay, so we've got a speed time graph, and you should know that the area under a speed time graph is the distance travelled, and we need to complete Harry's method to estimate the distance the car travels. So basically we're going to find the area of these two shapes and use it as an approximation as the total area or the total distance travelled. Okay, so how do I find the area of a triangle? Area of a triangle is a half base times height. So my base here is this distance, which is 10, and my height is this distance, which is 20. So then my area is going to be a half times the base, which is 10, times the height, which is 20. So half 10 times 20, well, half of 20 is 10, and 10 times 10 is 100. So that's 100 meters. Okay, so that's the triangle. Now for a trapezium, area is equal to a half a plus b times h, where a and b are your parallel sides. So basically you're averaging out your two parallel sides and you're multiplying by the distance between them. So I already know a, it's that 20. B is going to be this length here, isn't it, which is 30, and then the distance between them is going to be my h value. Distance between 10 and 20 is 10. Okay, so my area here is going to be a half 20 plus 30 times by 10. 20 plus 30 is 50, half of 50 is 25, and 25 times 10 is 250. Okay, so my total area under curve is going to be the area of the triangle plus the area of the trapezium, which is 100 plus 250, which is 350. And the units must be, what we've got, meters per second and seconds. So that must come out to be meters then. 350 meters. Question 24b. For this journey, which of these is true for Harry's method? Tick one box. Okay, it works out as an overestimate of the distance. It works out as an underestimate of the distance. It could work out as an overestimate or an underestimate of the distance. Okay, well, let's have a look at the method. Go away, silly thing. All right, so I've got a triangle here which is pretty much spot on, but my trapezium, look, when I calculate the trapezium, I'm not calculating this bit up here. So the true area under the graph is a little bit bigger than the area that I've calculated. So what I've calculated, this 350, is going to be an underestimation because I haven't calculated that bit there and included it in my answer. So it's an underestimate of the distance. Well, I hope this video helped you get a better overview of the topic. If it did, give it a thumbs up. You can find more exam question compilations over here. For more past paper walkthroughs, click down here. If you want to visit my Amazon shop with my recommendations for calculators, revision guides and other maths related stuff, click down here. Good luck in your revision and in your exams, and see you again next time.